So we're talking about the inversion technique here. So the purpose of inversion to uh, to use the geophysical data which is acquired from the field to improve our existing or starting geological model. And this is what we do. Why we do that? Uh, because probably the calculated response, which is a forward response of our model, and the observed response may not match accurately, which is most of the time it doesn't match. We can try to infer the geology from geophysical observations. We do it in an opposite sense. We use geophysical observations to try to infer the geological geological geometry. That's why we call it invert the previous process. Unfortunately, there is a problem with the inversion is uh, there is a there is a lot more solutions. There's a huge number of solutions that may provide the same response as your observed data. We call it non-uniqueness problem of inversion. There are certain way we can use to deal with the non-uniqueness problem. We will discuss this, how we can address these issues in the next slide. So the non-uniqueness and the multiple models, actually there are always a variation to the 3D geological model that still honor the observed data, contact and deep. If I explain it properly, um, when we try to derive a model with the help of observed data, algorithm may calculate thousand of number of model that will provide the same response. There is a number of models that may get the same response, but only one of them, or maybe few of the model, will be the accurate one. So our job is to reduce the number of models that we are getting out of inversion product. To How we can do that? We can apply some additional information, geological information, into the model to fix some of the layers, that this layer should not change during the inversion. So if we're providing some additional information, we call it prior information or constrained information. Inversion without constrained information, our inversion will be treated like a blind inversion. The inversion may give you any kind of geological model, which doesn't have any geological sense and probably doesn't have any correlation with your geological model. But if you're providing some additional information, such as drilling or any surface constraint or any subsurface information that you may rely on, that in that time, the inversion may predict few solutions that is most probable one. But we never support to return a single optimal solution, because this approach is not very useful. We call it deterministic approach, whereas a geomodeler uses Bayesian approach, which is based on the Markov chain Monte Carlo. This provides a statistical distillation of all possible model solution that give us a lot more information. That includes the uncertainty which is present in your model, in your predicted model. Here's the diagram that will give you how the inversion moves step by step, what information we provide. When we do the litho-constrained stochastic inversion, the first stage, what we do is we provide a starting 3D geological model, which is supported by geological observations. Geological observation, that means any drill hole or subsurface information that you already have uh, uh, collected from the field, or maybe this is already observed. So based on prior information, if you're building a model, that is treated as a constrained model. And this should be the starting point of your inversion to be performed. So in the beginning, the initial model, the reference model that we say is has to be honor all geological observations from your field, which is already available in your database. Then uh, uh, the model which is supported by gravity and gravity observations, there could be a possible model that supports your gravity observations. Suppose 1,000 model are supported the gravity observations, 1,000 models supported by the magnetic observations, and there is 1,000 model that supports the constraint that you have provided. The common model that supports geological constraint, geological observations, we say, magnetic observations, and the gravity will be treated as a most probable geological model that we're trying to find using the stochastic inversion. So this doesn't indicates any single model. There should be some there are few numbers of model that will going to be find using the inversion technique. Then we can try to we call it most probable geological model. Okay. So gather all three geological model which are consistent with the observed geophysics within a desired tolerance. Ready for the likelihood status. This provides the very uncertain how much uncertainty is available in your data in your final observation model. Your model never be treated as accurate, since it should always contain some uncertainty into it. This is one of the example from Bedbreath geological model we have created as a case study from the Southern Australia, the Victoria region. So initially, based on prior information from surface geological maps, drill holes, some basic understanding of the geology, we are able to create a starting geological model. In order to perform the inversion, the first stage is to discretize the starting model into smaller cell size, and okay, smaller cell size. Then we simply provide some constraint information that a particular formation can vary up to certain limit by providing the tolerance between how much variation we would like to accept during the inversion perform. There are certain parameters that we can fix in terms of commonality, surface, and volume ratio. During the demonstration, I will go through one by one and show you how these constrained geometrical parameter works. This may allow you to restrict the inversion to not change the geological formation, geological body too much, so that it get disturbed during the inversion outcome. Also, we can constrain, we can command inversion, we can restrict inversion to not vary some of the meaningful information that is accurate, whether from the surface geological maps. We can simply fix the surface geology from our model, so that it won't get changed during the inversion, because the surface map, it's kind of most observable inferred information that we get from the field. So we don't want this to be changed during the inversion. So if we fix this information, inversion has no right to change this information from this existing places. Same way, we can fix the drill hole traces, drill hole lithology, so that within a certain limit around the drill hole, our surface will not going to get disturbed during the inversion mechanism. Since drill hole and surface map are most uh, um, uh, uh, like accurate information of the geology, so we don't want this to be changed. This has to be honored during the inversion technique, and rest of the places where we don't have information, inversion will work on that reason. So for each formations that is converted into discrete cell, each cells contains the lithology information, which lithology it is refers to, and the density or susceptibility values, which are properties values, rock property values. And we allow some variation, a standard deviation within that limit, that the value of the density or susceptibility, so that inversion can select the most appropriate value under the probability distribution function that may help us to achieve the best fit between the observed and computed response. So here in this diagram, the formation we have created, that we have used in the bed geological model is like this, and this table indicating the density property values and magnetic susceptibility values, which contains the mean and the standard deviation of the density parameters or susceptibility parameters. So under this standard deviation, we allow some probability distribution function to be used for during the selection of the appropriate properties values during the inversion operations. The ultimate result will be the most probable density voxet that we get after the inversion techniques. That's supposed to be that's supposed to be highly optimized density of the geological model. The key consideration the inversion setup is we set the model resolution and the number of iterations during the inversion initial stage of inversion. We can set the geological constraint set as per lithology. Then we can also set the lithology property rock properties values under distributions. Then we can prepare the geophysical grids, and then we can set the survey precision of the geophysical data. Here's the summary of the bed inversion evaluation misfit. If you see, okay, it's not changing. Sorry. Hello? Anyone hearing me? Peter?
Yeah, yes, I can hear you fine. No
I
problem.
thought I lost you. Okay.
Uh,
Actually, slide was not moving that time. I thought, but I'm just going ahead. Okay, I have to repeat it again then. I was here actually. I have covered up to this slide, but I don't think you followed up to that slide.
well, we've seen this one. Yeah.
Okay, this is okay.
And this one.
Then okay,
Yeah.
here. So I was just discussing about the model perturbation, where we assign the discretized Fox at the each. Suppose there's during the initial stage of the inversion, we discretize our full model into the small cubes. Each cubes contains the geological information, that what formation it indicates, and the density or susceptibility, we call it rock properties of a particular cell, which will assign to this formation. This is a stratigraphic sequence of the bed model, and we can see the density and magnetic susceptibility values in the mean and the standard deviation of of each formation. So during the inversion, each the value of each cell will be decided based upon uh, 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 based upon uh, the random selection, which will be under the probability distribution function. The most appropriate value would be assigned to this cell or any particular cell during the inversion in the iterative process. The process is repeated in all cells interactively based on the number of iterations we have selected, and after the inversion, we'll get the most optimized rock properties model out of it. The key consideration of the inversion setup is we can set the model resolution. That's simply selecting the discretization cell size.
Prakash,
And
do you use that if you have, depending on whether you have a ground survey data or airborne data, matching the gridding of that data with the voxel size? Do you have any control over that?
No. This doesn't depends upon your cell size of your data. You can select grid cell size based upon your interest. There's no limit on that.
Okay.
Your data cell size will be resampled during the inversion operations for a comparison basis to compare your computed response with the observer. We put yes, I don't there's no like it is not required to select the discretization cell exactly the cell that you are actually having in your observed data. You can select any cell you
Okay.
want, right? So and the number of iteration that is indicated that is actually the number of iteration during the inversion iteration. Each iteration may contains the number of possible model that is going to pass the criterias of geological and geophysical and magnetic. We can set the geometric constraint per lithology, that how much variation we want on formations. And also we can set the rock properties distributions as set per lithology. Each lithology contains a specific value of density and susceptibility. We can set it and provide some variation like standard deviation based upon the confidence we have on the rock properties of each formation. Also the geophysical grid prepared and precision that we can set for calculating the misfit is the a summary of the inversion process of the bed model. This is actually showing the evaluation of the misfit. We able to see the vertical gravity ZZZ evaluation misfit curve and the total magnetic intensity misfit curve. And this portion here indicates the burn-in point, which actually reflect the misfit is actually going almost horizontal, and there's no much variation in this region. That indicates that we able to reach the optimum possible model, and our model is not changing after that. In this area, our model is changing drastically. Like model is changing, and up to this limit, we not able to minimize the misfit up to this like under this limit, So if we get the horizontal misfit curve, that indicates that our model is get optimized, and there is no possibility of improving the model. So after that, and this is a good indication if we're getting this profile that indicates our inversion has converged very properly. And same for the magnetic. And then we can set this limit of burning model set like burning point up to this limit to analyze what is the probability statistical distillation of up to this region, how much model is varying from this stage to this stage, to understand that if there is any changes happening into the model. The final result of gravity, the bed region, this actually indicating the observed GZ data, and the right one image is actually showing the inversion outcome on the improved geological model, and we're getting the nice correlation between both. I admit that there is a certain mismatch between the high frequencies, but this is okay. This is actually a very reasonable result. The same with the magnetic TMI. The observed one is actually matching with the modeled one after 2 million iterations. And this is actually a very nice study. If you see the evaluation of the model along a cross section, one of the cross section actually, this is a starting model that we have created using our understanding of the geology. After performing the inversion, the most probable model will look like this. You can see that there is a certain modification has been done after the inversion. You know that the intrusion, the which one, the Mount Lorach granite has expanded into the core, like expansion of the modern intrusions, and the initial model is slightly smaller than the in the starting model. But this is much improved, and we can see the geometry has been modified due to, after the inversion mechanism. So without having any further information or drill hole information, we're able to achieve the optimized model. Also, if we can mask the threshold limit, the probability of this model up to the 80%, that means the reason that is showing the color has an 80% confidence. You know, greater than 90%. And the rest of the areas, no, actually, sorry, this is actually indicating the confidence of the margin area, the inversion has a 80% confidence on that area. Rest of the formation, which is showing in color, has a 100% confidence on it. So these area we can treat as a like probable zone of interface, but still we have to accept the uncertainty of the prediction based on the probability statistic. We have at least some confidence, some less confidence over these regions that need to be reconsidered into your inversion. We can't tell in any case that our inversion can give you the exact model out of it. It always has some uncertainty in this model results. The probability model of the Rome supergroup, it's showing in this color over here. We can simply check each and every formation's probability, because our inversion result will provide you the table that has the probability probability of each and every formation for analysis. So just to recall, here's the workflow that how the Markov chain inversion algorithm works. We load the geological and the properties model in the initial stage. Then propose a single box set change to the model after discretization. Check that we still have the suitable geological model, but that means it will pass the criteria that of the the geological parameter that we have set in this in one stage. So it has to be past the geological criteria that we have set it. Then the forward model will be calculated and compared with the observable data, and the X is the likelihood to misfit will be estimated. Then if fails, it again go and set and select the other model which has a different properties based on random selection. Then again it will go and check the criteria of the geological constraint. Then again calculate the forward response and check if it is accept the modification or getting a misfit less between the computer and observer. And this is how it's continue operating throughout the different possible models, and only few possible models that passes all the criterias will be provided as a final solution. So inversion sequence, how it follow the step by step super summary statistics. We can analyze the result by most probable lithological box set that is provided as a final product, mean density of each and every formations, or as a cube. We will have an entropy that analyze the statistics of the probability of each formations. To test the stochastic inversion, we used to perform various steps. Like the first, we test a preserved vertical relationship that honors the stratigraphic sequences. It will allow us to restrict the relationship during the inversion scheme. Otherwise, our inversion will work very randomly and give you a very discrete and very weird result. Then we can set this commonality test that allow us to not vary our formation up with its shape. It will allow us to keep our shape common as we created during our starting model. Volume ratio, it allows us to restrict the volume, change in the volume of the formation. Shape ratio allows us to restrict the smoothness of the surface of the formation. And then the gravity misfit. This is basically based upon your formation lithology and the properties of the density that we have selected. And same for the magnetic misfit, it will compute the magnetic response based upon the susceptibility that you have assigned, and it will interactively select the most appropriate values of the susceptibility and calculate a forward response for as we've seen in the workflow. So the inversion result, how it does, how we see the step-by-step progress of the inversion, it's actually reflecting in this flow chart over here. So the initial iteration we have selected is around, like, you can select any number of iteration based on your requirement and your system performance. But in this example, suppose we have selected this 6 million iteration. In this case, the boundary the boundary condition is allow, like, half of the iteration is selected for the a boundary condition, which contains PVR, commonality, and shape ratio, volume ratio. The model which satisfy all these geological constraints will go to the next stage, where it has to pass through the geophysical gravity criteria and geophysical magnetic criteria. After the few model that accept these all criteria, that actually the pass these gravity and magnetic criteria, it's again enter into the boundary conditions, and the final result will be calculated based on that. So almost like 50 to 80% solution will be rejected in this process, and a few solutions will be stored for our statistical distillation. So what we get out of the litho constraint statistical inversion is this inversion is completely in three-dimensional, operate directly on an initial geological model that we have created that allow us to make any structure based on our interest. It also tackles the geological uncertainties. That is a most important aspect of any geophysical studies. Allows for geophysical data uncertainty in testing and refining the geological geometries and rock properties of the 3D model, as I said, and uses the gravity magnetic or both jointly for in the inversion scheme. The joint inversion is kind of more accurate than the single inversion technique, because there's two data set that allow us to that works to optimize your geological features, whereas only gravity or single gravity or single magnetic allows will perform only a single data, which may vary with the gravity model or magnetic model if we do separately a separate inversion. Okay, so it's kind of complicated presentation. So for inversion, we will use the same tutorial that we have seen in the last session, which is tutorial C. That is a very basic tutorial that help us to understand how this inversion technique works in GeoModeler. Since we have already performed the forward calculations, it will be easier for us to understand how the inversion will perform in the same model. This forward and inversion we should never treat it separately, but inversion is a kind of part of forward scheme that help us to improve our model on certain extent. We cannot use inversion to provide us the full geological model without providing any additional information to it. So I'm just opening the project. There's one project which is already have been created. This is sample model. And as I have demonstrated earlier, this model contains three major formations. One is a cover rock, second is a host rock, and third is a granitic intrusions. It's kind of batholith. The shape of the granitic body is this. And we also have cross sections that we can check how the shape of this batholith is along this cross-sectional line. So we what we'll do is we'll try to see how we can optimize this granitic body based on inversion technique. Since this body is completely based on our understanding, it doesn't have any information on the subsurface. So we have created this based on prior understanding of the geology. But if we try to optimize this shape of the granitic body based on inversion, we'll have to we have to understand what is the geophysical data that is available in this region here. I have, I have imported the gravity grid. This is a gravity grid, Bauer gravity grid. And you see the, the model response is actually beneath the gravity data. There's some correlation between the geology. I don't say this is not very accurate model. This is similar to what we are trying to achieve, but there are still some there's possibility of improvement in this geological structure. You see, there is a huge there is a high anomaly zone in this gravity area, which is currently corresponding to the granitic body over here. And because of this fault and the shift between the structures of the host rock, we are getting a slightly high anomaly in this region as well. Rest of the area has a low anomaly. So this structure is sounds reasonable, but let's see how we information, improve structure using this grid, this observed data. This is data. Okay. So initially what we need to do is we have to set, there's two kinds of parameter which is required for calculation of the forward and inversion response. Initially we have to define starting values of density or susceptibility, so that it it will be improved uh, when the inversion go forward, and it will get optimized after that. So we have to define the properties of density and magnetic if are working jointly. But in right now, I'm just going to define the property of the density. For the cover rock, I don't know, just have to I just putting some random number. 2.5, 3, 0.5, 2.5, and here 1. You may have think about why we have put it this values over here, 2.5, 0.5 interferation. There's a one more operation we can perform in GeoModeler to optimize your uh, to predict, to predict your density values or susceptibility values based on property optimization technique. This exactly work this work similar to the inversion. It will try to estimate the best suitable values of your density susceptibility, which can give you very similar response, like in the same range of the response as we have in our observed data. So most of the cases we don't have actually accurate physical properties information of the subsurface. In that case, this operation will be highly suitable for us, very useful for us. But in general sense, the cover rock has a will have the density around 2.2 to 2.35, but we have selected 2.5 in this case. I'll try to see what this property optimization algorithm provide us um, after prediction. I'm just going to click OK, and I will go to the forward wizard. I'll create one case, new case. Let's say I have used the gravity density values and I would like to calculate property optimization using the gravity data. I'll click next. Here's the density gravity grid that we need to select. This is a global gravity data from the which is the observed data. I've selected in this column and then click next. In this case, I don't want to calculate the forward response. I just wanted to optimize my density values that I have mentioned in our physical property boxes. I just wanted to optimize that. So it will perform 1 million iterations, and the difference with the trend between observer and computer will be matched by retraining it in the first order. Then I'll click next. This information, if you are calculating the considering the Borger gravity data, you should have information of the density values that has been considered during the Borger calculation, which is in this case 2.2 gram per cc. I'll use the same value for the above topo as well. So the property optimization is actually performing. The output will be a report file, which give you the initial property values, which is this 2.5 we have selected, 3 we have selected for the host rock, and 2.5 we have selected for granite. With this the standard deviation values like this. And after optimization, our properties get recommended by 2.28 for the cover, host rock around 2.63, and the granite should be 3.04. So this algorithm actually recommending to use these values in order to get the best fit between your observer and computer. So this way we can optimize our unknown physical properties, values of the formation, so that we can reduce the effort of multiple iterations. I'll use these values. I'll revise the physical property values by the optimized recommended values, which is calculated right now. 2.28. Let's use 2.2, 0.1, 2.65. This is around 3.1. Okay. So here's the revised values based on property optimization report. 3.04. Let's keep it 3. Okay. Okay, then if we calculate the forward response of the gravity, using the values that we have revised, so, we will able to get best fit between the data. Almost fit. The range is almost similar, pattern is almost similar, but we're still getting the misfit. Not a very reasonable misfit. We can improve it based upon inversion. But as of now, the density values is fine to be used for our further calculation, further inversion. We can do it same with the magnetic data as well. For the magnetic data, the optimized solution would be 0. This is susceptibility values in SI. So we have to keep the susceptibility values. Since this the sediment doesn't contain high susceptibilities values, that's why we need to provide the very low susceptibility values to the sediments. The standard deviation should be half, and the statistical law should be log normal. Since the variation is huge in the magnetic susceptibility case, that's why you use log normal distribution rather than normal distribution. Here, so we'll select the normal distribution, log normal distribution. And for the granite susceptibility is slightly higher. Okay, and the geomagnetic reference field. This is corresponding to the IGRF of that field that remove uh, the regional field response of from our data. If you're using the TMI grid, this is actually you'll get this information from uh, uh, international georeference and geomagnetic reference field values, which is published by agencies in 5-year duration. And this is calculated based on your project area location. So this particular values has to be subtracted uh, from your data to get the anomaly results. Now I'll go and execute the inversion using the physical property I have assigned. To improvement to show the each and every step of the inversion mechanism, I will move step by step. So you will analyze the importance of the steps that is going to be considered in the inversion and how it is uh, help us in improving the results. Right now, I'm just taking the case of the gravimetry, and then in the final stage, we'll choose both the data together to calculate the joint inversion. If I select the gravimetry and the rest of the things is okay, I will use the 2020 box set. This is fine. This is the starting value that we have set for our calculation. then this is the new thing. In inversion case, you will have this stage where you need to set the shared geological setting. The proposal, that means that once your smooth this model get discretized into several cells, you have to allow defining density values on the neighboring cell. If you're selecting this information, your neighboring cell will not going to assign not going to change the physical properties. So I'll recommend to not set this box in any inversion case that allow us to varies to change the physical property of the neighboring of the neighboring formation. The second option, the treat cell with the same properties law with the same methodology. This also is not required to be checked, since we don't restrict our inversion to to consider the same property law as the same methodology. The property law could be changed based on the inversion scheme, if inversion scheme is optimizing. So these two operations we can avoid to check. The third one is to probability of the property change only in percentage. This is the useful information that we can put. If we select the 50%, that means our two parameters. One is geology, the shape of the geology, and the physical properties, which is our density and susceptibility. So if we're selecting the change in the property 50%, that means 50% weightage will be assigned in the property change. Our property will be, the inversion will work 50% to change the property and 50% to change the lithology. If you're assigning to 100%, that means our lithology is not going to change in the inversion, only property will change. If you're assigning it to 0, that means only lithology will change, property will remain intact as we selected in the initial values. So this is how we can provide weightage on our confident basis. If we have a more confidence on our geological model, we don't need this to be changed too much. In that case, we can provide the percentage of the variation based on based on the value here. Or in case if you have a well information, log information of the density or samples from the drill hole data, then in that case we have a more confidence on the density or physical properties. In that case, we can use 0 percentage, so that only geology change during the inversion, modify during the inversion, not the physical properties. Then after that, let's keep it 50, because we have uncertainty. We have uncertainty with the physical property as well as geology. So in that case, we should choose 50%. Then next option is the fix the individual cell containing surface intersections. This option here to assign constraint information, to define the constraint information that you are using in your model preparation. If you're selecting this information here, any data that you have provided on the surface topography, either from geological map or any geophysical grids, any information that you have provided, that you have created using surface information. Most of the surface information is observable, you can see from your eyes, so you have a most confidence on those information, and you don't want this to be inverted or this to be modified during inversion. So you can fix those topographical information that you have digitized on the on your model. by selecting this option over here. If you have defined any particular contact, you can assign it here as well. So this contact can be in any section, cross section, as well as topography. And the point from CSV file that you have put it into the consideration, that you can fix from here and selecting the CSV file of a particular ethology. Contact with the provenance, this is kind of advanced feature. This actually comes when you define this already during your model creation. You know, every time you digitize one layer, you have an option to define that context with the appropriate provenances. If you have selected the appropriate provenances during the inversion, you can choose it to not vary. You know, you can choose it to consider during the inversion scheme by selecting it here. In case you have any well data, the well will be visible in this section over here, drill hole. And you also can include all the well information or any particular well information in the inversion scheme, so that your inversion can will have will have understanding that what lithology it should not like what the lithology around the drill hole can should not change. This is what option we have here. And next stage is to constrain to make a constraint of the geological formation. As I said, there's three major formations. One, constrain the lithology, then geophysical misfit, and like gravity and magnetic, and then the misfit calculations. This is what. So here we can set the constraint. That means how much variation we can accept on each formation during the inversion progress. You know, you can select on each and every formation, and accordingly you can set the commonality, shape ratio, and the volume ratio of each formation, so that we can restrict it to not get modified too much beyond the tolerance limit. So how it can be changed, we can select here and it will show us the parameter that we can simply change to restrict this information. Commonality, if we describe these terms properly, commonality, that means your shape, the shape of your body will not change, just like location will change, like it can move from here and there, but the shape will remain intact in that case. The shape ratios is basically the roughness of your model. If you want your inversion probable model should not give you the rough surface on the box set, you can restrict the standard deviation very tight, like 0.00 0.001, something like that. Otherwise, if you are allowing the standard deviation large, that means you are going to get a very rough surface of your predicted model or your optimized model. Volume ratio, that means if you want to increase your volume of formation during the inversion or decrease your volume of the formation during the inversion, you can set from here. So these options allow you to play around to control the geometry during the inversion scheme. Otherwise, if you let inversion work by its own, you will end up with a very random model. It is not very happy to see. You know. Then there is an option for the set the stratigraphic order. You always have to set the stratigraphic order during the inversion. Otherwise, all the formation will go and intersect with each other after the final calculations. So this we'll see one by one how we proceed with this. In the final stage, you select the iterations. That the iteration uh, depends on the volume of your data that you are using. If you are using the large iteration, that is fine, but that will take time. If you are selecting the large iteration, that will take time to converge it. So initially, I'll move uh, with a simple inversion without providing any geological constraint, any geological parameter, misfit, anything. We're not just it's a kind of blank inversion without any prior constraining parameters, something like that. I'm just using it, and this time I'm not going to provide any geological constraint. I'm also going to uncheck the stratigraphic order. So in this inversion case, I'm not going to use any like geological constraint parameter in this inversion. I'll see uh, how our inversion will uh, uh, like what product inversion will provide us without providing any constraint geological constraint parameter. So this is around 1 million iteration. I'm not going to check this. This is all unchecked. Okay. If I click next and just hit OK, what we are seeing is it's just working randomly, just selecting uh, 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 selecting the random number of density values, random number of random uh, 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 random model, and just giving you the response. Let's click OK. If I see the result here, this is your result without providing any constraint. This is actually a prior constraint inversion. This is my observed data, this is final data, and this is misfit. And if I see the product of the inversion, if I go here, right click over this, import geophysical result, case 5, run 1. Let's just hide the geology, and here we have a most probable model as a final result. We'll see it. This is your inversion model without having any constraint, having constraint on data. If I compare this with our initial model, this is look like this here. You see there is a like host work is going here and there. There's no correlation with the starting model. We'll end up with a very random solution. This is why we now this time what we'll do is this time we'll assign the preserve vertical relationship. I'll use the same case 5. Since this case is already saved, so we don't have to provide all this information again. It's already set. This is okay. This is also okay. This time I'm just going to use this PBR. I'll select this order and click next. And the same. I'm not going to use any of this information here. Okay. You're still getting the misfit, no control on the misfit. Let's see now what variation we get after this inversion scheme. Clone 1. This time, there is no like cross cut between upper formation and lower formations. All are separated actually, but still there is no geometrical correlation. Granite is very discrete, but preserving vertical relationship is actually work. It's actually work. Now we'll move to gain. I'll allow I will use some other criteria to be incorporated in this so that we'll again improve this model. And this time, what we'll do is we'll use the commonality. We'll use the commonality 0.4, that is fine. We'll use it 0.4. Click OK. And the shape ratio around 1, 0.01. Okay. I'm just going to use the commonality and the shape ratio in this, in addition to the stratigraphic ordering intent. This time we have chosen geological constraint to be considered in the inversion. Geological constraint to be intact, allow commonality and the shape ratio. Just include the rest of the thing. Click OK. This time we have restricted to not vary the formations too much during the inversion scheme. Inversion scheme 2. This is the clone 2. I'll use this final data. See, it is actually concentrated, but still it's discretized because we haven't allowed the misfit to be converged. If I project, so slightly we are actually converging it, controlling our geology based on these parameters. And GeoModeler understands our commands, what we are trying to do. So this way, we can use our data, observed data, to calculate the similar response by modifying it, our geological model, discrete geological model. Then again, I'll use misfit, shape ratio, that's fine. Okay. You have to sit. Okay. Stratigraphic order. This time I have selected the constraint to all of the formations. And now we'll calculate the geophysical misfit test. This sections is going to allow us to minimize to calculate the response of geophysical response of our model in order to minimize the minimize the differences between the observed and computed data. So here different things is happening. One is to predicting the geological change plus predicting the property change in in order to get the response which is similar to our observed data. So if the changes, if there could be a, like we'll start with the millions of models. We have like starting what we do is we have estimated the millions of models, and then we start using models one by one to pass through these criterias. First criteria would be to check the geological constraint. If some model passes this criteria, then it will go to the geophysical criteria to pass on. You know, if the values is minimizing the misfit from the previous one, then it will consider as a final solution. Otherwise, it will get rejected. This is how the whole iteration is going forward. So this time our misfit curve will be minimized, you know, if you're selecting this information. I'll click next. Click OK. Okay. So we haven't seen the progress of the inversion, but this is what the final result is of your misfit. This curve right now, it's going and converged uh, during the millions of iterations. You know, if I click OK, and now let's just check the product that we have calculated in the third stage of the inversion scheme. So this is our modified model, and the response of of this model is here. This is the final model after the inversion calculation. This is our observed final data, final response of this model, and this is the observed data from the field, and we are getting the misfit around 0.29 to 0.38, which is very reasonable. Initially we had a response like this here, and when we apply certain parameters, constraints, and and like uh, like minimizing the misfit consideration, then we end up with this result here. So initial, this is prior constraint, this is after constraint. Now we'll compare the improved result with the latest one, with the initial data. I'll project this results to the inversion. Here, what we see is the initial model is has slightly bigger shape than the optimized model. The updated model should be like this here. Should be like this. We can click the formations to see which formation is what. This is your inversion optimized data, optimized model of an inversion. It looks similar, but there's certain possibility to update this model and revise this model based on the inversion technique. So if I go again to the result explorer, you will see different things. During the forward calculation, where is the forward calculation? Here, this is the forward calculation of our initial model that we have used, and there is a difference misfit between computed and observed. But in the final model, the misfit has been minimized to the minimum, and we also get the uniform grid. Uniform grid, that's a discrete grid, but has a very low values of difference and almost similar response of final and observed data. Let's do a final run on gravity and magnetic as well by defining all constraint properly, and then we'll see what prediction we get with the improvement, and then we'll revise our initial model with the updated information. Then, so first we have to define the property. 6.3, I think this is fine, I guess. We don't have to change it. Then we'll go to the inversion wizard, and this time we will perform gravity and magnetic inversion jointly. We'll perform the joint inversion. Click next. Set the observed data, forward data. This is good. And again, we have to set the observed TMI data grid. Observed TMI data we already have. But this is to inform you that this data has been acquired through airborne, right? So we have to define a DREP clearance, terrain clearance, which is a platform on height, platform at some height where the magnetic data has been acquired, which is around 40 meters from the topography. So click next. I will use the same box set. We can improve it, but let's just keep as it is so that it won't take much time. Then we'll click next, and this time we have to set, we have to recheck again the density of cover rock, host rock, and granite rock. If you click on each and every formation, you're able to review the property values on normal distribution for density and log normal distribution for susceptibility. And if you want to modify it, just double click over it. You can modify it here from here as well. But we are happy with the parameter. We already have set it before, so it will just taking from there. And this here we have magnetic properties to set and gravity properties to set. And this time we are using density initialization from low mean. Low mean, that means I forgot to mention these sections actually. I just explain it again. Low means, that means the value that will be taken into account for the inversion initially will be a mean value. If the mean doesn't satisfy the misfit criteria, then it will move towards some other random value under the probability distribution function. But initial value should be mean. The preference always should be mean. If mean doesn't satisfy the criteria, then only other value will be selected. This is what it says. We'll use the reference density, the magnetic. I think the total magnetic fields has been already set. Click next. Okay, and again going to use the property change percentage 50-50 surface intersection, since there is no data available in the section, so it doesn't matter we check it or not. If we have utilized some map geological map and have digitized geological map on the topography, then only this will work. Our model doesn't have any surface topography digitization, so no, this doesn't make any sense to check. Click next. And this time we'll fix the lithological frontier. This we generally do with the uppermost formations, since the uppermost formation uh, always always observable on the surface. So we choose not to vary this formation much. In that case, we fixed it using this fixed lithological frontier. If we fix this, all the criteria for set the geological constraint will be hidden. So this is generally we do for the topmost layer. Other rest of the below layer, we have to define geological constraint. This is for the host rock. We're going to use host rock criteria around 0.1. We don't want our surface to be very much, so we'll choose very tight shape ratio. And for the granite, 0.4 and 1, this fine. And for the shape ratio, I will going to use the same values as we have chosen for the host rock here. And this time we can choose the volume ratio. It's up to us that are we going to consider this volume ratio during the inversion calculation or not. But at this point, just have to check this 0.1. Let's see. And for this 0.7, 0.1. Okay. So I'm happy with the settings. I chosen to not vary these formation much, just a granitic formation. I suspect this formation doesn't have a very large shape. That's why I have decided to reduce this shape of the granite. I'll click the stratigraphic order. It will select the appropriate order uh, to be honored during the inversion. Next, it's around 1 million iterations. I can choose to increase the iteration up to 2 million. And I'm going to use all this parameters. That means we're going to consider the geophysical misfit, and our model will has to pass the gravity and magnetic uh, uh, misfit criteria. In this case, also model has to pass the geological constraint that we have decided, that we have fixed through PVR and commonality, shape ratio, and all. So this has to be honored. There are few models will be that will pass this criteria and will stored in as a probable most probable model. If I click next, and then we can choose the number of cores based on your system, your system capacity. You may have core around 50, 60 core. You can choose the same, but in my system, I only have 4 cores, so I have to rely on this only. So you see the misfit curve is how it's actually working. This is actually the burning. We have reached at the burning point, and now we are our model is not changing much. It's getting almost parallel. This is the gravity misfit, and this one is the magnetic misfit. And we are getting a very reasonable result where we can see that the response is almost flat. after 1 million iterations. This indicates we have reached the stable model. Our model is stable and it is not changing after 1 million iterations. If I click OK, our model will store. Let's remove the previous model and import the new one here from import Geophysics case 6. So this is the case 6 run 1 final uh, case 6 run 1 final some uh, statistics result. We have a most probable model result here. If I project this into 3D model, we get this prediction over here. If I project this model to the sections, you're able to see the variation like this. Cross section C1, C2, C3. It's not changing that much. Still, we can improve it based on what we are seeing. To improve this data, what we can do, we can either digitize this model like here by pencil and assign this to the granite. Click on the associate so that it has the orientation data. And what I'll do is I'll remove the previous digitized model. This is my new data. This is okay, I guess, but we can modify this layer from here to here. Okay. And section C, this is almost good. I think we may we can improve it or not. That depends on us. Okay. Now I'll recompute this model so that the modification uh, can be uh, achieved. If I project new model, the model will be like this here. So it sounds good. Okay, if I remove this, or maybe this is our final improved model, but there are some problem along the such line. Okay. just trying to control the initial model geology, so that's why I have to create one another section so that I can digitize and control this geology. If I select all and update the model again, and then it's still not honoring. Okay, there's a problem. I have to select it all, then click. Right. So this is our final improved granitic body after inversion run. So I bring this most probable model uh, and mask the rest of the two formation and able to correlate it properly. This is the body we have, and if I launch the different geomodeler, so this is what the initially granite was, and this is the updated one based on inversion scale. And this results is based on joint inversion. If you see the result explorer, this is the result explorer, this is the gravity response, and this one is the magnetic response. The gravity and the magnetic response. And see that there is a reasonable fit between magnetic as well. The anomaly is around minus 0.99 to 16. And we have good match between the computed and observed. The gravity data has the same. This satisfy that our model is highly optimized right now, and we have the same response for gravity and the magnetic. Both data has been acquired in a different by the different technique, and hence if our model is satisfying both the data simultaneously, that give us more confident in our modeling result. So hope this is this is helpful for you to understand the application of inversion in GeoModeler. I'd like to invite if you have any questions regarding this technique, and any related problem that you have, that you are thinking to use this application, or you need any help on that, I'll happy to answer this.
Okay, thanks, Prakash.
Peter,
Nothing specific. There was a lot of new material for me in this to follow. So
yeah, okay. So Peter, you are a geologist, right?
yeah,
Yeah, okay.
yeah.
Uh, yeah, okay. Okay, so I'm just going to use some real field example uh, of this of implication of this method. One of the example from Indian continent that I have prepared personally, and there's one example from Australian continent, which is from uh, Broken Hill geological model. So this one is a Broken Hill data. I'm just going to use one test project to show you how. This is Broken Hill geometry, and this is not a good display of 3D model, because the render quality that I have used is so coarse. If I decrease the size of the cell below 200 meter, then we'll able to see very high resolution picture. But at this moment, that may take time, because this is a huge volume of model, and based on my system configuration, that may take time. The better I'll show you along one section, cross section view, so that you'll have idea about the complexity of this region under this. Okay, this is actually the location of this cross section. See, there's a huge fault going along. There's a highly complex terrain. Topography. Let's say this is, yeah, there's a uh, geological data that this does. If you have noticed that there are huge information we have marked based upon the surface geology. These all information are observed on the surface. So this whole information can be used to constrain the geology. We never wanted this information to be modified during the inversion. So this has to be intact. Rest of the information which is below the surface, can be modified based on inversion, because we don't have any accurate information up to that. If I show you the data, here, Oh, this is a surface topography. I wanted to show you the gravity data that I have. I'm going to import the 2D grids, and grid should be there somewhere. It's here. And, yeah, really well. This is options. Visualize on surface topography on histogram scale. This is the gravity data from the field. And see, there's a huge low dense sediment over here, which is a kind of uh, and high zone is representing the amphibolite cyst intrusion. So this is the image from, this is actually the model from the top and corresponding geophysical response. I think this is how it inclined, and this is actually what it says amphibolite gneiss, uh, which has been like uh, intruded, like it's kind of get get uh, stuck in by other metamorphic formations. And that's why it's showing the low values of the gravity, and these areas as a high amphibolite cyst that's representing the high gravity anomalies. So the result is, I'm just going to show you the result. Because I'm not going to spend time to estimate the inversion, perform the inversion. This is the forward response of this model based on the property has been used here. Most of the formation are either intrusive or metamorphosed. That's why we have taken very high density values of each and every one. These values are actually verified from the well data, so we can treat this as a most uh, suitable values. We don't want this to be disturbed during the inversion. That's why we have selected very tight standard deviation. If we go here 0.02, you see the likelihood of this distribution function is very low. This is why, because we have a high confidence on this values. We don't want this to be varies much during the inversion. So this is the forward response of the data, and the model has been calculated based on various cross sections and whale data. So we also rely on geometry as well. Thus, we need to have a little understanding of those area where we don't have the well data and the maps cross sections. So we have to use the inversion scheme to get the acceptable changes, acceptable change in shape on those area where we don't have the information. So the forward response of this model is actually providing the very similar response, not the accurate exactly same, but just a similar response. But we uh, still have like differences between the observed and computed. This is mostly because of some of the geometry is not actually up to the mark, up to the acceptable, uh, uh, the most probable uh, uh, label. So we need to modify it probably. So this will be done using the inversion technique. This is the example. This is the operation of the inversion result of the inversion scheme, and we see that there are a lot more modification has been done in the model using the uh, uh, inversion operations. We're getting almost the same response as we have on the observed data, and the misfit get minimized up to the minimum. In the real case, I think the, the range is highly acceptable because this is highly complex area, and achieving up to this limit of the misfit is also a very remarkable job. This was the initial model. I'll show you uh, the model after the inversion. This is the prediction of the inversion technique, and we can see there's a slightly variation between what we have used in the initial model and what we are getting after the modification. You see, we have limited this formation, the like what formation it is, the Alma niche up to this extent, and the inversion suggests that it has a deeper penetration. Some modification is required in this section as well, and here it's going from that reason, it has to be limited up to this region. So this is basically a kind of optimization of your model. So this formation has to be go from here. And this has to be limited from here. We can perform this inversion in the finer cell size, but this may take longer to 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 calculate the product, calculate the inversion product. But we'll finally end up with a very smooth model, predicted model that we can use for the modification. Hope this is okay with you. Now I'm going to move to the next case study. This is not the one. This one here. Let me just hide this. Okay. Just to show you, let me just show you first what are the data that we're trying to choose here. First of all, I just import the grid that we are using. Here is gravity data. This is a gravity grid. Not from here. Let me just open it. This one. This is a gravity grid, gravity image actually. Uh, Very vintage data, and we only have these contours uh, that we have digitized and extracted, then gridded it to get this whole block grid. And this is actually indicating a like a a regional basinal structure. There's not too much variation in this region. If we are talking about the regional scale modeling, just getting a slope along this region. This indicates uh, the basin area, and this indicates there is a large there is a like high density formation exposed in this area over here. If you open the lithology, this is it's a 1:400 K 1:400 K geological map of this area. This indicates the green area is actually is reflecting the highly metamorphosed exposed terrain, and the orange one is indicating the intermediate sediment that has been deposited uh, in Permian or some time uh, before Tertiary. And here, this area, it's actually a newer sedimentary deposits. So as we move from east to west, um, our like formation age is getting younger. So using this information, I'm able to create this model. Sorry. First of all, actually this is the shape of the basement that has been extracted using gravity data. We have uses this interpretation to prepare the basement. Final structure will look like this. Okay, this is not the old one. Let me just complete the whole dot. Put this in here. Yeah, this one. This is the final structure. Final structure using your basement interpretation as well as the information that we have derived from the surface map. Only 4 formation we have considered in this model. If you see in the inversion technique, sorry, in the define this one. Okay. If I open this cross section over here and plot this setting, you get similar some structure like this. This is a highly random structure that I have created without having any information of the surface. Just the information we have is it's getting deeper along this direction. We don't have the control under the depth. That's why I've just taken a straight line, and I'll let inversion to modify this layer based on the gravity data that we have. We finally able to end up with this result. Let me just open another project, final project. I'll open the section number 3. Section number 3. Disappear. And this is the final model after the various updation from inversion or forward modeling. This is what we get after improvement. This is previous model that we have put in. How to validate this? If I see the response along the profile, let's go to here and use this to trend grid. Can compute. This is what the response of the forward. This is the geology, and the black one is our gravity data along this section, and red one is the forward response of this model along this section. And this has to be similar, this has to be exact, like it has to be follow the same pattern if we are getting this good geology. Whereas if we go and compute the same vector for section 3, we're getting the good result over here. So I suspect that we are in a common section, but it is section number 3. It is section number 3. The geology is too much different, but the responses are different than too. Section 1. Let me just open the section number 1. Section 2. Yeah, this is okay. Okay. But this is what we have earlier. This is what the response of the initial model, and this is the response of the final model after improvement using inversion technique or the forward technique along the line. If I show you this is the updated one, and if I show you the results, you get. Let me just open the observed data grid so that you can compare it side by side. Yeah, this is the observed data, and this one is the final computed response from the inversion, and this is the misfit of between observed and computed, and the result is from inversion iterate case number 8. And you can check that the parameter that has been assigned 2.67 is above total, and the layers, what are the density parameters, distribution we have considered, and for the middle, all the information whatever we have used during one inversion case is stored in this section for review. And this is one of the very nice simple model example which we have done in a using a real data set. Which if you see there's a elevated mountain over here. It's not clearly visible. Let me then what I'd have to do is just if you see there's a nice mountain chain along this direction that supports that there's a huge sedimentary sequences. which is getting elevated due to the compressional force from the lateral side. Suppose that there's a basement, there's a huge sedimentary deposit. Okay. So this is the last example that I wanted to show you that. And I just one more thing is left to discuss the FTG, full tensor gravity gradiometry application in GeoModeler. This is just one case. I'll just go quickly and show you that. Open. Full tensor data, we can use full tensor data in a various way. One is to select any particular component and execute a forward and inversion on that particular component only, or we can use all the components simultaneously to execute these operations. Full tensor or partial tensor may be probably the, if you talk about specifically the tensor data, AGG data, airborne gravity gradiometry data. Generally, contractor provide us a 6-component, which contains horizontal components, vertical components. There is a 5 independent components and 1 TZZ component. I'll show you that. Here. Generally, we used to have these 6 component. East component, east north component, east down. East means like X, let's say X, Y is north, and D means down, that means Z. So we generally used to provide, contractors used to provide these all components. So it is better to utilize all these components together in the inversion calculation. You know, because of sensitivity of the tensor data, we may get a highly accurate optimized result as compared to standard conventional gravity magnetic dataset. So there's no doubt that tensor has like far more better information as compared to the normal dataset. So yeah, the inversion will work very accurately when we use the tensor data. Let me show you one data that we have from tensor. This is tensor data FTG trip. Okay. Here, this data contains like this much of this many components. Like components should be the 6. The raw components, it's a 6 component. The rest of the information are the derivatives of which has been calculated using this combination of these 6 components. If I project this TZZ data, I selected it, and then I project this on crystallography. We have a high sensitive response over this area. Since TZZ is kind of like total vertical horizontal, a second order derivative of, which is equivalent to the second order derivative of the conventional gravity data. So we get a very cellular response of high frequency response of the geology, which is very sensitive. And due to this sensitiveness, we able to optimize the model highly accurately without even providing much constraint into the data. I'll show you one example without using much constraint, how we able to get this information. So this time I'm going to use, I'm going to create a inversion case. I have already a case saved, so I'm going to use it and show you what are the parameters we have chosen. So in this case, we are selecting all the 6 components. Since our data has all the 6 components into it, so we can use it directly. Or if you want, if you have only one single component, then you can just select any of those or maybe multiple and perform the inversion on based on one particular component only. I have all the ones, so we are going to use all of the components together. Then click next. The first thing we can load the tensor data set into it. And this the observation error, which is standard 0.1. In this case, you may decrease this observation error to the minimum, lower than this as well. Then the drep grid. This is actually a data from this is actually a data from um, the zone, the plane where the airborne has where the aircraft has been flown during the acquisition of the data set. So this is actually an important thing to provide, since ArcGIS data is highly sensitive to the height. So we have to ensure that our platform should be uh, 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 like we should mention the height of the platform so that we're able to compute the inversion on the particular platform only. So whatever the computation will be done on this platform, this reference height. The vertical control interval, this has to set 50. This can be changed based on your interval, based on your grid cell size of your drep grid. This time the inversion has been taken on 50, 40, 14, 42 meter height, 42 number cells, which is we're going to compute a finer cell size or better calculation. The density of value of this formation has been taken the same as we have chosen initially, 2.2 for cover. Post rock, we have chosen the bimodal distribution this time. Bimodal distribution, that means 0.5 gram per cc for the 90% of the formation and 2.9 gram per cc for the 6% of the formation. Sometime, like in some kind a spatial condition, or in case our particular formation has contained the bimodal or dual nature of density. Suppose there's some intrude, some like composition is so complex that it reflects two density, two types of parameters, two types of properties. In that case, we can assign different values to particular formation based on the concentration of based on percentage of the component which is existed in the particular formation. And for the granite, we have chosen 3.1 gram per cc, just the same, and the standard deviation 0 in this case. We don't want to change anything else. The power anomaly is 2.2, 2.2 reference density for this, and we're going to treat the property change only percentage 100. That means you're going to change the property 100%. Let's do it 50. And click next. And this has been fixed because this is the uppermost cover. Host stroke has been assigned. The commonality is very tight, 0.2. And the safe ratio is also tight, 0.01 standard deviation, which is supposed to be very, it's not going to allow the vary the formation much. And the volume ratio is the same. Okay. So click the stratigraphic order. Click next. 6 million iteration. No, this is not 6 million. Less than 1 million. Okay. They're going to allow the preserved vertical relationship test. Rest of the criteria we have not used in this case, just to see what will the response. Since we are using all components, though it's supposed to resolve the geometry without even providing much constraint to the geology. Let's see the response. So we're performing the inversion. I think when we use the tensor components, it doesn't require much time to import the data, since there are sufficient information that resolve that going to select the best probable model instantly. So inversion doesn't have to work that long. So in the case of tensor, the convergence is quicker than this conventional data set, and the accuracy is far more better than that. Okay, so okay, this is going to take time now. This is only 2%. So I should display the existing result that we have calculated. Just let it go like the same way. I'm just going to open this. So this is the result of this is the result of the same case that we have executed. Actually, the past record of the result. The current result is going to calculate it very soon. And this is the final updated model using the FTG data. If I project this along the section, okay, this is actually already updated. Project. So the green one is actually the modified model after the FTG inversion. And see, this this become modified a little bit better than the gravity data that we have used in earlier case. And the red one is actually reflecting our previous model. and the green one is the inversion model that has been calculated using the FTG data, full tensor data set. Here, you can see that model is get more concentrated in this region, and the earlier model was highly like something like this here. So what we did is we have digitized this and updated the formation. This is why we are just able to see the green here. Here, you can see that how much variation are there in the granite data from the previous model and the updated model. If I project this here, in 3D view, this is a particular density model. And this is the final product and most probable model using the inversion. I'm going to mask so that only granite can be displayed. The granite number is 1. If you have a problem to identify what is the numbering of your ecology, then you can go to here, stratigraphic file visualize, and show the current model. This represents the numbering of your formations, and it says the granite series contain number 1. But since we are here in this lithology, it's showing that the 1 formation, the green one, is actually in 1. So I'm just going to display 1 formation number 1. This is the most optimized shape of the granite. Since the AGG data is far more accurate, we're able to converge, to optimize the granite, the particular body to the high, to the better limit. And if you check the and this is the response from tensor data. Since tensor is very sensitive to the geological formations, we'll see that there is a high anomaly and there's a sharp low anomaly zone because of the fault heap. And then again we're getting some values along this region here. The tensor components is slightly different than this. If you check the TZZ component, it will show us this image here. Similarly, for TXX, this is the TXX grid, which is getting similar. Misfit is low. On TXY, this also looks good. So what we have here is we kind of doing a combined inversion using all the 6 components. If all 6 components giving the same response as the observed one, there's no doubt on the geological model that it is not probable. You can also compare the derivatives of using the tensor data as well, such as total horizontal gradient amplitude, which is actually highlighting uh, uh, the fault zone, highly fault areas. So we're able to compare all the grids simultaneously, all the products simultaneously to validate our inversion model. So as of now, we can say that this is um, a highly reasonable model, highly updated model based on the data we have used without having any drill hole or any seismic information up to it. We're able to achieve the accurate shape of any block or any formation. So up to this stage, you would like to discuss any point, please let me know, Peter.
No, that's fine. So this is actually you have the gradiometry survey over the same area that
Yeah, yeah.
previous data was.
If
So it's good
Mhm.
for comparison.
Correct. So yeah, probably if your area has the HEG data, then you can do this operation to optimize your model. Yes, I agree that we don't actually find everywhere the HEG data. It's kind of costly operation, but it's a highly accurate when if we use HEG data for the optimization. You know the if we talk about the regional scale, sorry, the prospect scale model building to predicting the mineralization zone, as compared to attempting the drilling, we will get cheaper cost of acquiring the data from HEG as compared to the drilling. So
Mm.
this is basically upon the what is the best way uh, to understand the geology, just understand the geometry of the subsurface. And some people actually used to do this kind of study before go for the large scale drilling operations. So these are the geophysical applications of the geomodeler. And then we have already seen the geological modeling operations using geological data. Then we have seen geophysical application in the geomodeler. And one more thing left is the groundwater applications. We'll see how geomodeler can be used to estimate the meshes, various kinds of meshes, and interoperability with these meshes with the free flow and other environments. How we can uh, use geological model uh, uh, to help understand the reasonable resource and water modeling kind of operations, and with the help of both the softwares. I'll see it in the next session. And I'll also like discuss, as you have pointed out in your email, if you have any data, we can discuss it in this session or maybe next session after the end of our training, or maybe uh, for 30 minutes. So to understand what is your objective and what type of data is available to you, and what further work we need to do to make this data readable to GeoModeler. And
Mhm.
then we'll plan forward to how we uh, prepare some exercises based on your data which is available to you. So can you give me some idea about your objectives, why you are uh, what is actually your uh, uh, objective of your organization? So what kind of operation you used to do as a geologist?
Oh, well, there's a whole group of geophysicists who use their own software for surveys which are acquired
Mhm.
both within house and the national airborne surveys which were completed many years ago. So there's a lot of geophysical expertise there,
Okay.
but there's not a lot of we
Understood.
say this iteration between the geology and the geophysics.
Oh, yes.
There's also
This,
seismic.
uh,
We have a lot more to extract from regional deep seismic surveys as well, in
yeah.
which the
I think
gravity and magnetics are. But
the point.
my particular interest is in uh, structural controls on mineral deposits. So it's building detailed uh, geological models and then using them as well. Again, it's the iteration between the structural styles of known deposits and then how they assist in exploration. So this forward
So,
modeling and
okay.
inversion capability is very valuable, I think.
Yeah, yeah. If you're talking about the mineral prospecting, then these operations could be helpful uh, to predict the elongation, like what is the extension of your mineralization, and what could be the volume estimation of that we are where to drill the next target. This kind of details you can find out without having initial drilling information, just using inversion technique. But yes, there's a lot of thing in inversion that we need to learn. Um, there's like, yeah, we need to make some assumptions and predictions, prior information required to guide our inversion algorithm so that it won't get some superstitious results. So that is need to be carefully evaluated first before we go for. So can you tell me what data do you want to use uh, in like mineral exploration kind of, that based on your objective? The data you have is well data, or what data do you using?
I have geological, structural, lithological information in geological maps. There's several case studies or regional studies which I would like
Okay, okay, that is
to bring
helpful.
into GeoModeler.
Yeah,
Yeah.
yeah, that is helpful.
Then Christian, I'm sure, has many other ideas.
Yeah, sure. So as of now, what I shown you is um, GeoModeler has no limit on the data integrations. Whatever data that help you to build a model, you can simply use it in GeoModeler. Either it is map, seismic, drill hole, any shapefile, or geological cross section, or any data. I mean, there's a if we cannot directly integrate into GeoModeler, there is some way around we can simply integrate it. But whatever information we have, we can integrate it in GeoModeler. So maximum information will leads us to build a high confident model initially, and then we can interactively update those model based upon the additional information that is going to be collected in the future, in afterward acquisition plan. So this is completely interactive process. If you have some geophysical data, then you can also apply into this software to update it to revise your model, update your model, and then there is operations to do is to calculate the volumes, identify the shape, estimate the grades. This kind of application we can use to identify the mineral potential of that particular region. So this is a complete workflow what we actually do with the GeoModeler. So I heard from Sarah that you're trying to integrate some geological modeling operation with GeoModeler, and you have some. Uh, do you have any idea uh, what
Well,
is your
two
objective with the groundwater? Yeah, please.
there are two projects at the moment where it's I would be looking at both the two ways of building the GeoModeler. Uh,
Mhm.
One is just from surface map and structural data, but I also have made my own guesses at cross sections. So it would be just in the one area would be trying to build a fairly complex, it's geologically complex, but geometrically relatively straightforward. So for
Okay.
testing a, a complex folded stratigraphy with granite intrusions, and so to build a structural model of that, and it could start just with uh, digitizing from the geological map of the cross sections. So there are two project areas where I
Okay.
think of that, and
Perfect.
one is which I'm trying to negotiate whether we would work in cooperation with a mining company.
Nice. Okay. Uh, sure. That's fantastic. Perfect. Regarding your, if you have any data that you want to work on, uh, uh, during our sessions, if you like, if you have those data set that we can use to learn to get familiar with the software, that I may help you with this.
Okay, thanks, Prakash. Then, if Valu is still present, then the next session will deal with the groundwater.
Yeah, yeah.
And have you been able to, or you and Seda decide when that next session would be?
Next session means regarding groundwater, probably the Monday, I guess. But I think it should be. What is your availability? Let him. Can you tell me that so that I can.
Uh,
You have to check or
next
what?
next week I'm traveling a bit, but it'll be more
Okay.
be particularly for the two people who are interested in groundwater, Vala and Maria Amelia.
So if
So
you know if they're available on
if I
Monday,
could
I
suggest to them uh, what day next week would be most suitable. We have actually some
okay,
in-house business meetings through next week, but
okay,
from
okay.
my point of view, Friday would be fine, and uh, and
Except
Monday.
except Tuesday, I'm available whole week
Yeah.
except
Okay.
Tuesday.
I'm just checking mine and Mary Amelie's calendars.
Mm-hmm.
Uh, maybe Thursday morning looks good. And yeah, on Monday, Maria Amelie has a morning meeting.
Yeah, because of the time difference, then it's
Yeah, yeah.
we need it in
Yeah,
the
I'm looking
mornings.
at the I'm looking at the morning. So it looks like next week, maybe Thursday is the best.
Next week
Okay,
Thursday.
I would think, yeah,
Yeah, I
and I
think
would
I'm
suggest
okay.
that.
Yeah, Peter.
Okay, uh, I might have a meeting on Thursday, but the most important is for for the groundwater experts. So for Vala and Maria Emilia to, if it suits you, then let's suggest Thursday then.
Yeah, I told you
Yeah.
I'm fine. Except Tuesday, I'm fine with every like I'm available a whole week except Tuesday. That's fine. I think we can conduct this session next session on Thursday. But if there's any sudden change, if you decide to reschedule it, please let me know.
Yeah,
Otherwise,
yeah,
I will discuss with Seda and send you the invitation next week Monday for the session.
yeah.
Hope
Okay. Well, thank you.
everything is
Yeah.
okay.
Right.
Okay,
Okay.
and
Thank you very
and
much
then
again,
Peter,
Prakash.
I think Peter, your availability should be important because we have to discuss about your data set, didn't you?
Oh yeah, 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 yeah. I'll see what I can do there. At least for the early part of the session, it should be possible.
Sure. Okay.
Um,
Perfect.
and then I will also have a chance to visit the offices in Melbourne and see Seda on uh, sometime at
Great.
the end of the month. Be going to Australia. So,
Perfect. I think you're going to enjoy it. Okay. Great. So, that's it. I think rest of communication will be done through Sheda. I'll let her know about our discussion, and after
Yep.
the session, probably there is one more session for our discussion regarding data set and projects related work, right?
Yes.
Okay, okay. So we'll come with another date for this. I think
Yeah.
I'll have to collect more information from Seda. What need to be discussed during that interval? Probably Seda will
Yeah.
ask you about your data set, detail about the data set and the project related information. Then we'll see
Yes,
how
that
we
might be.
conduct. Perfect. Okay then.
Okay.
Perfect.
Thank
So
you.
thank you so much for your attention.
Thank you, and a good
And
weekend to all of you.
Have a
Right.
nice day. Bye.
Yeah.
Thank you very much.
Bye.
Thank you
Bye.
for hearing the painful presentation. Probably I'll bring some next nice interesting slides in the next session for the ground modeling.
Good. Thank you very much. Right.
Thank you.
Bye.
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 Bye all. Bye. See you all.
Bye.
Thank you so much.